Okay, so Dr. Hassan, this report on quantum sensing, it's like actually blowing my mind. It's not just theoretical, right? Like this stuff is really happening?
Absolutely, Emma. It's truly groundbreaking. We're talking about a paradigm shift in how we observe Earth. Traditional sensors, satellites and radars, they've improved, but they have these inherent limits. Quantum sensing, it just offers unprecedented precision, in measuring things like gravity, time, and light. It's not science fiction anymore. It's operational. Prototypes are running, missions are being prepped for space, and even commercial products are out there in the energy and utility sectors. It's really exciting.
Wow, that's wild. So, like, how does this actually help with weather prediction, or climate modeling? What specific kinds of, I guess, quantum sensors are we talking about here?
Well, it's about getting incredibly detailed data. So, for example, we have cold atom interferometers. These, they measure tiny variations in gravity. Think about applications like tracking groundwater depletion or mapping ice sheet changes, crucial for climate science. Then there are optical clocks. And these optical clocks, they're just amazing, Emma. They can detect gravitational redshift differences to measure height with centimeter accuracy over vast distances. So we're talking about refining global height reference frames, getting super precise sea level monitoring, which, as you can imagine, is absolutely critical for coastal climate resilience, right? Japan and Europe have already shown portable versions working across hundreds of kilometers. It's really happening.
That's insane. Centimeter accuracy, like across huge distances? And what about you mentioned gas detection earlier, like methane plumes? How does quantum tech help there?
Ah, yes, that's where quantum LiDAR and single photon imaging come in. These systems dramatically improve sensitivity for detecting gases like methane, which is a huge greenhouse gas, obviously, and for atmospheric profiling. So we're talking about really precise wind measurements for weather modeling and understanding fine-scale cloud structures. The UK, for instance, has QLM, which has commercial methane sensors in utility projects. And China's even got a prototype quantum wind LiDAR. It's not just theory, Emma. These are tangible, working technologies.
Okay, so we've got gravity, height, and atmospheric gases. What about space? I saw something about spaceborne quantum labs in the report.
Oh, the spaceborne quantum labs are crucial, like NASA DLR's Beagle on the ISS. It's all about providing long microgravity timescales to really mature these cold atom technologies. We're preparing the groundwork, the technology base for future quantum Earth-observing satellites. Multi-user experiments have actually already started in 2025.
That's so cool. So, who's like leading the charge on all this globally? Is it mostly Europe?
Well, Europe, especially France, the UK, and Germany, they're definitely at the forefront in commercialization and space missions. They're leading in spaceborne quantum gravity with missions like Carioca PMP. But, the US and Japan also have substantial research depth. Japan, for instance, is a global leader in those optical lattice clocks we talked about, and it's critical for their sea level monitoring efforts. Australia and Canada are carving out really interesting niches too. China, for its part, has strong prototypes, especially in quantum wind LiDAR, even if their commercial traction isn't quite at the same level as Europe yet. It's a very collaborative, yet a competitive landscape. It's all moving so quickly, it really is.